Okay, so last time we did a one-way analysis of variance and we did the four steps. And at the end of the four steps, we rejected the null hypothesis. Now, with ANOVA, you have the regular four steps of the hypothesis test, but then there's a little extra step that we do after the F-test. So what we're doing in this video is after the F-test. So I'll just recap what we did when we conducted our test. And then the two things we need to do are talk about effect sizes and this thing called post hoc tests. And that'll be a new concept. And so we'll talk about sort of when, why, and how. And I'll show you talk about three different versions of that, because there are like a dozen different methods we could use. But we'll focus on one developed by a guy named Tukey, and it's called HSD. So we'll actually conduct that one. So importantly, this is still ANOVA. And it just, because of the complexity of the analysis, it has more steps than t-tests. So anyway, before we begin, you might hit pause and make sure you're ready for this video. We need the completed tables from video 3A and 3B. We will introduce a Q table. This time it is in the same document with the F table that I linked on the Moodle page. And we'll do some calculations. And at some point you'll hit pause and maybe do some calculations yourself. So here we go. As a recap, in our test we had three groups: the block, word, and Stroop color naming conditions. The alternative is at least one is different. We used the F table to establish a critical area. In step 3, we filled in the source table. It shows the sources of variance, and we found 11.43 for our F. And because that is definitely past the critical value, we rejected the null hypothesis. And the null hypothesis is basically, that at least one group is different. Okay, so as I said at the end of the video, we don't know which groups are different. It could be any combination of differences, and so we need to explore that a little bit. Just kind of want to remind you, though, what we're doing conceptually here is that when we calculate total variance, what we do is we get the sums of squares for everyone, and we ignore what group they are in. But then we calculate between groups variance, which is based on how far apart the means are, and then within groups variance, which is the variance for all these individuals. And then we add up for each group. And what we did with our F test is we found a significant F value, meaning that the ratio of this type of variance to this shows that more of our variance is coming between conditions than among the groups or within the groups. So what we're doing with the effect size questions, we're asking how much variance exactly is due to the between groups variance. And so I kind of wanted to show you again, between groups variance is when you calculate the sums of squares for the means. So this would be the distance between the word group mean and the overall mean. So you would square that distance, square that, take that distance, square that, add them up, and that's what is sums of squares between. And so what we're working on now is finding out, like, if that sums of squares between is much greater than sums of squares within, how much of the variance is actually due to that. So the statistic we use there is called eta squared. This is the Greek letter h, lowercase, and it's squared because it's dealing with sums of squares. And you can see this is just a basic proportion. It says, here's how much sums of squares we have in our study. Here's how much we have because these means have split up. Okay. So what I'm going to do is go back to the source table. I got a little screenshot right here of our source table from the last video. And you can see that our sums of squares are right there. So I'm going to take the sums of squares between groups, that's our numerator, sums of squares total, that's our denominator, and that gives us 0.718. So literally what that tells us is that almost 72% of the spread in individual scores is due to the fact that our means are pushing people apart, not just the fact that people might be a little different than each other. There's some rough guidelines here. These are not like strict cutoffs, but generally speaking, if you have an eta squared that's down here in the single digits, what it's saying is that only about this much of the variance in the study is due to the means. So that's kind of smallish. If you're up in the teens, it's going to be medium. If you get above 0.2, 0.25, that starts to be pretty big. And so needless to say, this is an enormous effect size, and one that you don't get that much in research, because usually in research you're not exactly sure what you're going to find. I set up something that I knew would give us a big effect. So anyway, that's how you do the effect size. So when you have a significant test, whether it's a t-test or z-test or ANOVA, what that's telling you is that you probably have a reliable difference. And so the effect size comes along and says, not only is it reliable, but it's probably there because it's big. The alternative is you can have a reliable effect only because you have a huge sample size. So it's good to know that this is a serious effect. When we have an ANOVA, the second thing we have to do is figure out what is happening with our group means. And this is called a post hoc test. So with the post hoc test, what we're trying to do is when we reject the null hypothesis, we say one mean is different. We need to figure out which mean. So when do we need them? If you reject the null hypothesis and k, the number of conditions, is equal to or greater than 3. So we need them because our k is equal to 3. We have 3 conditions, and we rejected the null hypothesis. And this is because F tells us if there is a reliable difference, but this post hoc testing that we're going to do is to tell us where the difference is. So if you remember that idea about having several ways of comparing these groups, we have 3 groups, so there's 3 different comparisons. We need to know which of those are significant. So here are the 3 that I just wanted to mention. We're going to do Tukey's test, the HSD test, because it's a pretty solid one. You can do it by hand pretty easily. I do want to show you the Bonferroni one because it conceptually makes a little bit more sense. It's kind of hard to see what Tukey's test is doing. And I want to mention this Scheffé test because in the literature, such as your reading assignment for one-way test, they use the Scheffé. You're going to see Scheffé a lot more in journals, but it's kind of hard to do by hand, so I just want to show you that one. So conceptually what it is, an easy way for us to do it, and then something that you would do if you were using SPSS in reading. All of these are just members of this group of thing called post hoc tests that you use to follow up an analysis of variance. And what they all do is they let you make multiple comparisons without alpha growing into a huge number. So if you remember in the first ANOVA video, I said the reason we do ANOVA is because if you were to make all those comparisons by t-tests and used a 0.05 alpha each time, at the end of your experiment, you'd have this experiment-wise alpha that's much bigger. So what Bonferroni decided to do a long time ago is he used this formula to figure out how many comparisons you'd want to make. In our case, we'd have 3 because we have k is equal to 3. 3 times 2 divided by 2 is 3. But remember that grows really fast. So 4 goes to 6, 5 goes to 10, and so on. All right, the next thing you do is you create an adjusted Bonferroni alpha. So you would say, I want my experiment to have an alpha of 0.05, and I want to do 3 comparisons, right? Because we want our alpha to be 0.05 and we want to make 3 comparisons. So if you just split that alpha into 3 groups, then what happens is if you reject the null hypothesis for each of those 3 comparisons, you would have only a 0.05 alpha rate at the end of that. Now that works okay. I hope you see what that's doing is it's kind of distributing your risk tolerance across different groups. The problem with that is that it gets really, really hard to reject the null hypothesis every time you add another condition. I just want you to stop and look at that and make sure you understand how that works. So anyway, it's a 3-step procedure, and we won't be doing this, but it's super easy to understand. Finally, post hoc tests sometimes create what's called a critical value of a significant difference. Tukey's version is called an honestly significant difference. There's another one called a least significant difference. But the method here is that when we're going to actually do something like a mirror image t-test and wind up with a critical value that's actually in the units of seconds. So get what you need. We'll need the table from class 3A with the means and standard deviation, a source table from the previous video, and that's from step 3, and then a Q table. Okay, so here's how you do Tukey's test. The first thing you need to do is calculate HSD. HSD is a straightforward formula. It's Q, the mean squared within, and the n per condition. So the first thing we'll do is look up Q. So if you have the Q table, you should see something like this. I've added some labels to it to help. First thing we're doing is we're looking at the number of conditions, which is 3. The degrees of freedom within is 9. And that says 3.95. All right, so these statistics, I know they're kind of hard to understand, but this is kind of doing what a t-test would do in reverse. It's kind of weird. All right, so 3.95 is our Q. I'm going to go to the source table. We need the mean squared within, which is 3.9. And the n per condition, I had 4 people in each condition. Remember, there's 12 overall, 3 conditions with 4 each, so that's 4. So when I run that, I got 3.9 as my HSD. Okay, so HSD is 3.9 seconds. That's our critical value. What that means is we have to have a difference between 2 groups of 3.9 seconds for us to say they're significantly different. All right, so this is my table from step 3 of my ANOVA. This is, we did that preparing for the ANOVA. So what I'm going to do over here is I'm going to just show all the possible differences. The block group is 8.3, word group is 7.3, and so the absolute value of the difference is 0.57 seconds. Block versus Stroop, the difference there is 5.8 seconds. And notice I don't care about the sign here. We don't need to know if it's positive or negative. Word versus Stroop, 6.05 seconds. So that is all of the possible comparisons we can do. So now what I'm going to do is use my critical value of 3.9 seconds. And what that tells me is that the blocks and the words aren't really honestly significantly different from each other. That's probably just some random error and individual differences and things like that. So 0.5 seconds is not significant. Now, if you look at the other 2 down here, though, those 2 wind up being significant. So 5.48 between block and Stroop, 6.05 between word and Stroop. Anything over 3.9 seconds is significant. So 5.5 seconds and 6 seconds are definitely significant. So, in conclusion, what I can take from this is that the block and Stroop condition are different. The word and Stroop condition, basically the Stroop condition is different from the others. And so I can go back here to this text, which I wrote at the end of our F-test last time, and add to it in red that eta squared is 0.78, and that a Tukey HSD procedure showed that there were differences between the Stroop condition and the others. Okay. Now, normally you would also refer someone to some statistics, either in a table or in a graph. I just chose to put figure 1, even though I haven't created that yet because I thought that would be a bit much for one video. All right, so that is it. As you can tell, there's a lot that goes into ANOVA. I have classes 1, 2, 3A, 3B, and 4, and all those together should get you set to read and conduct ANOVAs.